Hi everyone, today we're going to do an introduction to algebra. So algebra deals with unknown values. The word algebra refers to the title, comes from the title of a book, an Arabic book, titled The Science of Restoring What is Missing and Equating Like with Like. And that describes algebra quite well. We're going to start though with restoring what is missing, which is working with unknowns. Now, when we learn algebra, it draws quite heavily from arithmetic, operations, fractions, inequalities, tables. We use all of those sorts of ideas, but with a focus on finding unknown values. Now, in primary school, typically unknown values are denoted with a box. So let's have a look at a simple case. So here's a case, box plus 1 equals 3. We can discover the value in the box by inspection, or typically we call it guessing. And in this case, we can see that the missing value obviously is going to be 2. 2 plus 1 is 3. And inspection is great for simple cases. So box times 2 equals 6. It's quite obvious that the box is going to be 3. And box divided by 5 equals 5. We know that from the 5 times tables, 5 5s are 25, so 25 divided by 5 will in fact be 5, so the box will be 25. But the problem is that for complex cases, inspection is not great. So we need some tools that are going to help us find the boxes for more complex cases. And we're going to build up to that. But first we've got to establish the conventions of algebra. So we're going to do that through some examples. Algebra is often used for modeling cases, and we're going to model some natural language problems using algebra, and we're going to sort of build up to it looking more algebraic by the time we finish. So here's the first case. Johnny has some marbles, and Jack has double the number of marbles that Johnny has. How many marbles does Jack have? Now, there's not enough information to answer that question with a value. All we can do is make some statements. So in this case, we're going to let box equal the original number of marbles that Johnny has. So that allows us to write how many marbles Jack has. Jack has box times 2, double what Johnny has. Now we work on a different case. If Johnny loses a marble, show clearly how many marbles each has. Well, Johnny started with box number of marbles, and he's lost one, so he has box minus 1. Jack was defined by the original number of marbles that Johnny had, so Jack has box times 2 still. He didn't lose any marbles. He's got the same as the previous case. Now we still don't know the quantity that Johnny had originally, but if we did, we could substitute the value into the equation. So let's imagine that he had 10 marbles to start with. So at the end, Johnny would have his 10 marbles and subtract 1, which would give us 9 marbles. And Jack would have double the original 10 marbles. He'd have 20 marbles. And we could do that for any value or any quantity in the box, as long as that was the relationship between the marbles that Johnny had and the marbles that Jack had. Now, using boxes is unwieldy, it's hard to say, and when algebra was described in print, it was hard to print a box, but it was very easy to print letters because books have letters in them. So we started to use letters in substitution of other variables or other things for unknown quantities. So when we use a letter for an unknown quantity, instead of calling it a box, we're going to call it a pronumeral or a variable. So here's a case where we're doing that. We're looking at the same case we were dealing with here, but this time instead of boxes, we're going to put letters. So in this case, I've used the letter X. Let X equal the original number of marbles that Johnny has. The number of marbles that Jack would have is X times 2. So that's really what this is saying, but now with an X instead of where the box is. Now if Johnny loses a marble, show clearly how many marbles each has. Johnny has X take 1 because he's lost 1 marble. That's the original number of marbles he had. And Jack's still got X times 2. Now we can say let X equal 10. Everywhere where we had X before, everywhere we had X, we're now going to put 10. So 10 minus 1 and evaluate it. That gives us 9. 10 times 2. And that will give us, when we evaluate it, 20. Still doesn't look very algebraic, though we do have these letters now, so that kind of looks like algebra. Now we've got to look at some of the conventions of algebra. So conventions in algebra typically are to not use the multiplication and division symbol in most cases. So instead of x times 2, what we're going to do is we're going to say 2x. And when we've got a number and a variable next to each other, we're going to assume that we're multiplying, or that's implying that we're multiplying. We can swap the order because multiplication is commutative and order is not important, but order is important with division, so we have to be a little bit careful when we divide. And instead of using the division symbol now, we're going to use fractions instead. So instead of saying x divided by 2, we're going to say x on 2. We have to be careful because 2 on x, order is important. The first number is the numerator, the second number is the denominator. So 2 on x is not the same as x on 2, in the same way that half is not the same as 2. So order is important with division. The other thing that we need to do is when we're multiplying and we have to substitute where two numbers are adjacent, we use brackets to indicate multiplication. And that's more obvious with the example that we do. So this is the same case, but now we're going to use these conventions. So x take 1 stays the same, but instead of saying x times 2, we're going to say 2x. We still substitute with let x equal 10, and 10 take 1 equals 9. But you can see here where instead of saying 10 times 2, we're going to have the number in the front from the 2x times by the 10. We don't put the times anymore, we just put a bracket. And 2 times 10 is still 20. So these are two important conventions of algebra. It just saves us writing extra stuff. It's simpler. Now, here's another case where we model a situation. So Jill has a lemonade stand. It costs $25 to set up the stand. She charges $3 per cup, and each cup costs $2 to make. How much profit does she make from 10 cups? And when will she make a profit? Now, it's a bit of a leading question. We can sort of tell from 10 cups she's not going to make a profit, and then we've got to find out where she has to make a profit. But without algebra, this question tends to be something that would be a page full of random stuff that kids write, and it's not very systematic. And what we're going to try and do is work towards a precise and systematic way of recording what it is that you're finding out. So let's try an algebraic way. The first thing we're going to do is we're going to write out all the unknowns. And in actual fact, there is only one unknown, that's the number of cups and the profit. But it does help us if we write out revenue and cost separate. And we do this a lot and increasingly between year 7 and 12. So it's quite good if we start now. So n equals the number of cups sold, p is the profit, how much she makes, r is the revenue, so how much money she takes from customers selling the cups, and c is the cost, how much it costs to make the cups in the first place. Now profit is always revenue minus cost, and in this case we know the revenue is 3 times the number of cups, so each cup is $3 times by the number of cups. That'll get you how much money comes in. And the cost is equal to $25 to set it up, plus $2 for every cup. So $2 times how many cups you make will give us the unit cost of the cups plus the startup cost. Now profit is revenue minus cost, that's what we said here. So revenue is 3n, there it is. Cost is 25 plus 2n, and we subtract them to get the profit. The 3 dots over here just means therefore. It's another mathematical convention. So we can do this without algebra. In the case of 10 cups, the money received for selling 10 cups would be 10 times $3, which is $30. The cost for selling 10 cups would be $25 to set it up, plus 10 lots of $2, which would be 25 plus 20, which is $45. And the profit would be $30 take $45, which is a $15 loss. No great surprise there. If you don't sell enough cups, you don't make any profit. If we're going to do that with algebra though, instead of writing all of this out, we would write the relationship, write the substitution, do the substitution, evaluate it, and then write the answer to the question. Now you can see that rather than all these words, we're writing less and we're saying it quite concisely. So this solution is precise, it's simple, and it takes away the vagueness of natural language and any extra operators. And that's what we aim to do in mathematics, make it simple and precise where we can, so that anyone can understand it. Now, unfortunately, without learning further algebraic techniques, which we'll do shortly, finding when a profit is first made, so whether it's 15, 20, 50 cups, requires guess and check at the moment. We'll have more algebraic ways to do it and systematic ways later, but for now we're just going to use guess and check. So if it's not 10 cups, let's try 30 cups. Well, if we substitute 30 into our profit equation, we find out that we make $5 profit. Brilliant. But that's not the first time we made a profit. We probably made a profit before that. So what we should do now is start to record that information systematically so that we don't just have numbers all over the place. So a table is a good way of doing that. N is the number of cups, and P is the profit for the associated number of cups. We're making some coordinates here, some ordered pairs. So for 10 cups, it's negative $15 a loss. For 30 cups, we made $5 a profit. And so we've shown this last case in here. Now, if we did n equals 20, we substitute 20 into both equations. 20 into the right-hand side of the equation in both places. And we find out we make a loss of $5. So the profit point is probably somewhere between 20 and 30. And we've recorded that in our table. Now, typically when you're doing this, you'd have your scientific calculator there, and you just keep filling out the table. You wouldn't keep doing this each time. This is overkill for what you need to do, but it's good to show how it all works. So my next logical case would be somewhere between 20 and 30, which is 25. And we find out we make zero profit. That's our break-even point, where we start to make a profit in the next, when we sell the next cup. So here we are. We've sold one more cup, and now we've made a profit. So we can see from our table, the first profit occurs at n equals 26, and it's $1 based on the data collected. Now this would be really difficult to do without a systematic way of writing it down and working it through. But once we're confident in our algebra knowledge, the solution might look similar to this. Here's the question. Here's the definition of the unknowns. Here's the relationship between the unknowns. Here's the relationship between profit and number of cups. Here are the findings when we investigated a range of cup sizes. Here's the statements that answer the original question. How much profit does she make from 10 cups? Negative $15 a loss. When will she make a profit? When she sells 26 cups. And a profit would be $1. Quite a neat little solution to a quite difficult problem at this stage of understanding algebra. So I hope that was helpful, and I look forward to working on the next one with you, where we start to look into algebra in a bit more detail. Thank you, everybody.